webinar series. For those of you that joined us yesterday, thanks for coming back. And if you weren't able to join us yesterday for the first webinar in the series, that webinar has already been posted. Thank you, Susan Brulette, to our website. So if you want to go back and watch it because you weren't able to catch the webinar yesterday, it's available for viewing. I'm sure Susan will drop the link in the chat at some point today. We put up our first poll, and please feel free to fill that out while I'm doing introductions here. Just trying to get a sense of who's on the webinar today. Oh, there's Joshua. Hi, Joshua. Glad you can make it.
Hey, Heather. Yep.
Great. So again, welcome back to the second webinar in the Soil Health Indicators webinar series. As I mentioned yesterday, this is a 4-part series focused specifically on the indicators that we're all evaluating to let us know if our soils are healthy or not. The webinar recordings can be found with the link on the screen, and I think Susan will drop it into the chat as well. Just a quick thank you to my colleagues that are joining us for the webinars, and also to Susan Brulette, who helped us organize this today, and to NRCS CIG program that's funding our work. There will be one CCA CEU Soil and Water Management credit available at the end of the webinar. So if you just wait at the end, you will be able to scan the QR code. Okay, so the webinar today will be with Dr. Joshua Faulkner. And I like your title, Crushing It. Did you come up with that, or did Lindsay?
Lindsay.
It like a Lindsay.
That's all Lindsay. Yeah.
Yeah, I was gonna say that sounds like Lindsay. Anyway, but I love it, Crushing It. He'll be talking about soil physical properties and the soil health indicators that help us understand how the physical properties are functioning in the soil. Don't forget, our third webinar is tomorrow with Dr. Deb Neer, and she'll be talking about biological indicators. And then the last webinar will be on Monday, December 16th, with Caitlin Hicks from Dartmouth, and she'll be talking about carbon and different carbon fractions and the indicators that we look at with carbon and soil health. So without further ado, welcome to Dr. Faulkner. He's a research associate professor in the Department of, it's not plant and soil science anymore, it's agriculture, landscape, and environment at the University of Vermont. He also is a part of the extension system and wears many hats, including the director of SHREC, which we did introduce yesterday. So people are really excited about the new soil health lab. And so Joshua, I think I'm gonna stop sharing my screen and I will turn it over to you. And we ran out of time yesterday for questions. We had some technical difficulties today. Hopefully we'll have more time for questions. And you can type those into the chat and we'll ask Joshua at the end of his presentation.
Okay, great.
Okay.
Thanks, Heather. Can you screen look okay? Are you looking at the right thing?
Great.
Okay,
yep.
Awesome. Thanks. Yeah, so kudos to Lindsay for the awesome title. Very clever. I'm excited to talk about these physical properties and how they relate to soil health, and it's just so closely related to a lot of the research I do. So it's exciting to be here, part of this webinar series. So I'm going to start with texture, go into structure and aggregation, talk about bulk density and compaction, and then hopefully I'll have time to talk about another physical indicator, available water capacity, which I think is becoming more and more important in Vermont. Even though we have these wet years, we're seeing more drought as well. So if we have time, I'll do that. And I ultimately do hope to leave some time for questions. So let's go ahead and get started. So we'll start with texture. And I think this is where any discussion about physical soil health indicators really has to start. This is just such an important factor when we think about physical factors related to soil health and the role they play in soil function. When we talk about texture, we're really referring to the various proportions of three different types of particles, and those are clay, silt, and sand. And I'm guessing many of you have seen this soil texture triangle here on my screen. And this just is a very clever way of defining how we label a soil's, how we define a soil's texture. And you can see as you slide clay on the left and silt on the right and sand on the bottom to their varying proportions, you cross the lines and you have a you know what soil texture you have there. And so I think we all have some understanding of that. These different size particles, these different particles, sand, silt, and clay, are one way in which they're dramatically different is in their sizes, and this is this figure kind of relates them in terms of their relative size differences. Where if we think about a sand particle being the size of a barrel, then a silt particle is a plate sitting on top of that barrel, and then a clay particle is a very small coin sitting on that plate. And so these are hundreds of orders of magnitude different in terms of their size, and that plays important. That means they play in the size is an important factor in how these soils function. One way in which this makes a difference is clay. Although clay is very small, it has tremendous amount of surface area and is also negatively charged. So the higher clay content you have in a soil, it means it has higher cation exchange capacity. It holds on to nutrients better. It also holds on to soil organic matter better, which is something that we're going to talk more about here as we talk more about aggregation and soil aggregates. And then another important factor here is that the size of the particle really influences the void space or the pore space within the soil as well. And this is not only the pore space within a soil aggregate, which are very small pore spaces, but also the pore spaces between aggregates when you stack aggregates up within a soil volume, how big those spaces are, and that is the size of those spaces is I would argue as important as the size of the aggregates themselves, because those pore spaces play such an important role in regulating biota movement, air movement, water movement, nutrient movement with that water. So these are kind of the master control, this texture factor when we start to talk about physical soil health indicators. And it's not just the physical soil health indicators they also influence some of the other biological and chemical soil health indicators. But one of the primary ways I think we think of texture in soil health indicators is in terms of infiltration. And I think we have an intuitive understanding of this. The coarser a soil is, the coarser the texture, the higher our infiltration rates will be. And the finer our soil texture is, the more clay content we have in that, the lower our infiltration rates will be. This is, I think, well understood. But what may not be as well understood as that is that how these different textural classifications affect other soil health indicators. And this is kind of a figure that's a combination of the Cornell Assessment for Soil Health Scoring System, which is this kind of red to green color-based indicator scoring system, and a study that was done in Ontario just recently, where they compared hundreds of soils in Ontario and determined how they aligned with this textural-based classification system for soil organic matter. And you can see here we have 3 different lines. These are normal distribution functions of coarse soils, medium soils, and fine soils. And what this really means is that if you take a soil organic matter of 40 milligrams per gram, which is about 4% by mass, and you take that line straight up, that when you hit that fine textured line, about half of fine textured soils will be greater than that, and about half will be lower than that. So it's but then if you go on up to the coarse textured line, you see a lot more coarse textured soils are going to be lower than that 4%. So what this essentially means is that it's much more common to have a fine textured soil with high organic matter than it is a coarse textured soil. And so we score a coarse textured soil much higher when it has the same organic matter content as a fine textured soil. Texture, here's another good example where this matters, and this is evolved CO2 or soil respiration is what we might call this. And you can kind of see the same relationship emerging both in that Cornell soil health scoring system and also within the data points from Ontario, which really matched up very well with these normal distribution functions from the CASH test. What about Vermont? So this is, I hope some of you are familiar with the State of Soil Health Report, which was a fantastic study led by Alyssa White a few years ago, published in 2022. I think we can get that link out to folks if you're interested. But this is a look at how soil texture classifications are related to active carbon or permanganate oxidizable carbon across Vermont soils. And you see that relationship similar to organic matter and respiration if you move from the left to the right, where your coarser soils have lower active carbon, and then moving up to your loam soils, which are kind of higher than the coarser. And then we have this interesting thing happens where we start to get into more of our clay soils, and our active carbon goes back down. So this is really interesting. I think this is really good foundational information for us in Vermont as we continue to study soil health and build on our database and start to understand why this is happening, why we see lower active carbon in some of our finer textured soils, which is maybe not what we would expect to see as we look at these national databases. Okay, so that's soil texture. Now I want to jump into soil structure, and as defined, soil structure is the combination or arrangement of primary soil particles into secondary units or PEDs. And so I think of soil structure in 3 broad categories: microstructure, mesostructure, and macrostructure. And I'm starting here with microstructure, some really cool images of clay particles, these platy clay particles that have very clear structure when you look at these with a high-powered microscope, especially the image in the lower left. And these are bound together by polysaccharides and proteins, and they create pore space. And that's really part of what's most important here, is that pore space that you're seeing develop as the structure develops, creating space for biota, air, and water. And of course, in a water quality sense, where I do a lot of my work, this structure has a huge impact on how water moves through the soil, and any dissolved substances like nutrients or colloidal substances that go with that water. Here's some more images, and this is really highlighting how other types of biology affect soil structure. These are fungal hyphae holes within the soil structure, which are creating what I think of at this scale, kind of macro pores within the soil. I think it's interesting that you see these formations, these macro pores at this very small scale, and they look very much like what you might see in soil structure at a larger scale, what you can see with your naked eye when you see root holes and wormholes within the soil. Again, these are really important, not just for transmitting water, but also for holding water. And I think here is where we really start to see some of those organic materials, the polysaccharides and the proteins, the glues that are holding the soil particles together. So just some really cool images to look at. And I think Deb, for this slide, this is a slide she uses in our soil health lab talks around aggregate anatomy, and just gives us some good information on what are the constituents of soil aggregates. If you start there at the bottom with the smallest size aggregates, I know it's a little tough to see, but that's 0.2 microns, and those are plates of clay and organic materials that are acting like glue to hold those together. And then we work on up the size ladder from 2 microns to 20 microns to 200 microns and 2000 microns. And we see different types of biological materials forming the hyphae and the bacterium and the fungal debris start to form aggregates with the inorganic materials. So kind of the key point here is that these aggregates are not just mineral matter, sand, silt, and clay, that they have a lot of the composition is of the biological materials as well. And and then here on the right hand side of the screen, microaggregates being less than 250 microns. And those really one of the important pieces here is that the pore diameters in microaggregates are much smaller than the pore diameters within the macro aggregates. And so that means that they create different types of habitat for different size organisms and different abilities to transmit water and air. Here's a nice high-powered microscopic image of a micro aggregate. This one, you can see all these kind of funkiness that exists within this. There's mineral matter in there. There's organic matter, and it's all kind of held together in this micro aggregate, which again, we bring all these lots of these micro aggregates together to create an aggregate, and those aggregates are then come together to create larger soil structure. And that's what I'm attempting to show here, that we have these individual particles glued together to create aggregates, and those aggregates are then stacked together within the soil profile to create soil structure. And those aggregates are typically what we can see with the naked eye, which you can see kind of there in the lower right hand corner of your screen, the soil crumbs, if you will. Those are mineral particles and biological particles as well. Here's a photo from just a really great photo from a farm I used to work with in South Hero, that I think shows, and this is a clay soil and just really nice aggregation within that soil. Here's another, I think, Deb, for this slide as well. And this shows the composition of these smaller micro aggregates coming together to create medium-sized aggregates, and then those medium-sized aggregates together to create a larger aggregate. And really, again, where you have different size pore spaces that are going to function differently in terms of the type of biology that they're going to foster and enable to exist in there, and the different soil or water and air flows that can occur in those spaces. So how do we really measure this aggregation thing? I think we're all aware this is very important in terms of soil function, but it is difficult to measure. And the one way we do this is to look at the stability of the aggregates. And by definition, aggregate stability is how well these aggregates resist breaking apart when exposed to external forces. And those external forces are what you might expect: raindrop impact, forces from wind, human forces like tillage, mechanical forces. And then I would also include internal force, quote unquote, internal forces. And that's what we're seeing when we see this Slake test on the right. And maybe some of you have seen this where we have a really well aggregated soil, strongly aggregated soil on the left, and a much poorly aggregated soil, weakly aggregated soil on the right. And we put this into a water column. And if you think about kind of that soil being dry with lots of the pore spaces being empty, there's actually tension with, or a vacuum, if you will, within those pore spaces, and it pulls water into those pore spaces when you submerge it in water, and it reduces that soil tension, or in other words, it increases the pressure within those pore spaces. And those pressures, if the aggregates are not strong enough, will break apart the aggregate. And so that's what this is a really clever way of visualizing how strong your aggregates are. And these are not really those external, I don't think of them as external forces. I think of them as internal forces, but these are important, I think, for us in Vermont, especially as we think about flooding conditions and climate change, and the more frequent we're seeing, how frequently we're seeing our soils become saturated, that some of that saturation can break apart those aggregates within the soil profile and create silt, sand, and clay particles that can migrate and further block pore spaces lower within the soil profile. So with aggregation, I think we often think of this as helping to prevent erosion from that raindrop impact. Raindrops hit the soil surface at about 32 feet per second. That's their terminal velocity, give or take. And when they do, they're like, if you kind of imagine a meteor hitting the surface of a planet, like we've seen cartoons, and it just blows chunks of stuff everywhere. When raindrops hit aggregates, if they're not strongly aggregated, they blow that aggregate apart into those individual constituent particles, the sand, silt, and the clay, and those settle back onto the soil surface. And it's like, I think about it as if you had a big vat of baseballs, which are your soil aggregates, and then you blow apart some of those baseballs into BBs, and you poured those BBs into that vat of baseballs. Those BBs would find the pore spaces within the aggregates and fill them up. And that's what we get when we have surface crusting. And that's when water ceases to infiltrate into the soil and increases the erosion. And there's lots of ways, or lots of data on how just pure physical cover can help protect those aggregates if we have weakly aggregated soil, or even if we have strongly aggregated soil. Here's a good example of some data showing just as we see percentage of soil cover increasing, that infiltration increases in turn, and runoff decreases. And that's just really just a physical protection of those soil aggregates. That is shown also in other data with in terms of long-term management. Here's just a conceptual diagram showing how a long-term sod versus a long-time cultivated soil, which is well managed, versus a poorly managed cultivated soil that forms crusting or surface sealing, and you can have many times greater infiltration within the sod or the well aggregated soil than you can within the crusted soil. This is a great example of that occurring in visible to the naked eye. This is a rainfall simulator that I used to drag around when I worked for Extension in the Chesapeake Bay watershed, and I'm going to focus here on the left. And these were two soil samples taken side by side in a cornfield, and one just has some physical cover on it, some mulch on it. Then we rained on this, and you can see such a difference in the amount of water that runs off of these soils and those buckets in the front versus how much water soaks into those soils because those aggregates were protected, and those are the buckets in the back where you can see, there's lots of infiltrated water in the soil that had the straw mulch on it. And then of course, it's not just the runoff volume that's important here, it's the actual soil loss which you can see in the jar on the far left. And of course, that's not just soil, that's nutrients that come with that soil as it runs off. So just a really great visualization of how aggregates can be broken down if they're not stable or not protected from raindrop impact. And then I can't do a presentation without throwing in a picture of a gully. So here's one of what ultimately results at the landscape scale if we have really poorly aggregated soil and we start to surface crusting occurs and we start to channelize water, and eventually we see these things occurring, these gullies occurring. So aggregate stability in the lab. How do we know this is very important? How do we measure this? And there's really three different ways that we do this. And the result of all of these is really a percent of the mass of soil within that sample that does not fall apart under pressure, under forces that are exerted on it in the laboratory. The first way here on the left is using a rainfall simulator, and this is how, if anyone sends samples to the Cornell Soil Health Assessment Lab, this is the way they assess aggregate stability. They have this rainfall simulator that they stage above samples on sieves, and then they rain on those samples. What I think is more common is a wet sieving approach, and this is a device shown in the middle. This is one way of doing it. There's other devices that are used for this called a dunking apparatus, where you have multiple sieves stacked up. This is what we're doing in Shrek. And you kind of move those sieves up and down and exert some force on those sieves from internal forces or forces from the water, and see how the different size classes of aggregates stay together. And then the third method, which is pretty slick, there's been a lot of work done on this lately by the Soil Health Institute. This is the SLAKES app. I just had a chance to use this recently at a conference, and pretty interesting. There's some good papers comparing this to the other methods if you're interested in taking a look. But what this does is uses a cell phone application with imagery, and you look at the aggregates when you first submerge them in water, which is those three red dots on the left, and then you look at them sometime later. I believe it's 4 or 5 minutes, something like that, and it analyzes how those aggregates have crumbled or fallen apart within that, within as they're submerged, and then calculates an aggregate stability index. So very, very interesting. This is something you can actually do, at home very easily on your own farm if you wanted to do, if you didn't want to send samples to the lab. Okay. So that was microstructure and or mesostructure, and now macrostructure. So we have these aggregates and they're all put together in the soil profile, but then we have kind of somewhat inherent soil properties, especially at deeper depths, that create macro soil structure. And this has a large influence on how water moves through the soil as well. And these are some of the different types of different terms we use to describe macro structure, and we have some of these in Vermont. Some of our clays are prismatic, and they create these vertical pathways for water to move very rapidly. And these are great. These are useful terms, but I think when we think about management, we really want to think about structure in terms of bulk density, and this is the structure within that zone of management, say the 0 to 12-inch layer, where we're actually actively using equipment, and the majority of the root zone exists for our crops. And so soil bulk density is just the way it sounds. It's a measure of the mass of soil within a known volume. And the way we typically do this is what's shown on the left here. There's a metal cylinder of known volume. So for example, this may be 2 inches long, about 2 inches in diameter, and we pound this into the soil, and then we remove it. And within that core, we have this relatively undisturbed sample of soil that we then dry in the lab, in the oven. and determine what the mass of soil is within that known volume, and that's our bulk density. In general, we're looking for, as you might imagine, lower bulk densities than not. Typical bulk densities hover around 1.3, but I've found, and others have certainly found as well, that this is highly variable based upon soil texture and also based upon soil management. Here's some more data from the State of Soil Health report that looks at bulk density as a function of cropping system. And this is, I show this because how interesting, how it really shows the variability in bulk density. And what you're not seeing here is, if something is in corn, what are the management practices associated with that particular cornfield, or what is the soil texture within that cornfield? But you see this wide amount of variability across these different types of land uses. And then as it varies with management, we have some general expectations around bulk density as it relate in terms of as a function of soil texture. And so here's some reasonable guidance, I think, for different soil textures: sandy soil, silty soil, and clay soils, of what your ideal bulk density would be for plant growth, and then what bulk densities would restrict root growth. And I think what's interesting here is we see both bulk densities ranging from, in a clay soil for ideal, from 1.1 all the way up to a restrictive bulk density in a sandy soil to 1.8, and that's a really wide range. So texture, here's another example of where texture really matters, and understanding what your expectation should be around bulk density based upon texture is very important. So bulk density, of course, in practice, and we have different ways of trying to preserve bulk density and reduce bulk density, from no-till to zone-till, strip-till, ridge-till, different ways of disturbing that soil less than we would with a full-width conventional tillage that would destroy aggregates and allow those soil particles to pack in closer together, increasing that bulk density. And that has real implications for soil loss and water loss, as you see here on the right-hand side of the screen. What we're also seeing here is not just a difference between a high tillage and a no tillage, but we're also seeing the influence of a cover crop as well. Okay, where I think the rubber kind of hits the road for us in Vermont, in many parts of Vermont, is with soil, with bulk density and soil structure, is what we call soil compaction. And this is, again, I don't know that I need to explain this, but the soil is composed of mineral matter, excuse me, air, water, voids, and organic matter. And when we have a compacted soil, we've crushed those mineral particles closer together, so we have less room for the air and the water and places for biota to exist. And this is, I think, especially prone to occur given current conditions in Vermont with climate change and just wetter springs, wetter early summers, where people are trafficking on their soils, and soils are staying wetter for longer periods of time. This figure here shows what I think is one of the more onerous forms of soil compaction, is that deep soil compaction, where we have where the soil is moist, the pressures underneath the tractor tire travel deeper and deeper into the soil because the highly moist soil transmits those forces downward. Where in a dry soil that does not necessarily happen. Compaction also affects water infiltration and water runoff, and is also influenced by soil texture. Here's an example of how a compacted soil or a native soil what infiltration rates would be within those soils in a sandy soil versus a clay soil. And then most importantly, in terms of yield, in terms of production, compaction also affects yield. And you can see on the left-hand side of my screen, a compacted soil, what that will mean for root growth versus an uncompacted soil, and then some work done in the Midwest, actually measuring yield reduction due to compaction, where we have yield reductions up to 42% in a heavily compacted soil versus an uncompacted soil. Measuring compaction. So this is a very real problem here in Vermont with our soils. I think this is much more challenging than we admit. I think that we're typically using a penetrometer. I would advise caution with these tools. The advice is that you measure penetration resistance when the soil is at filled capacity. I think that's really difficult to determine in practice. Primarily, we have, because of the recommendation is to measure it, 24 hours after a rainfall event in a clay soil. That in a loam soil, that may be fine. In a clay soil, that could be 2 to 3 times longer. If we're not actively watching the rainfall, we don't really know what the moisture status is of our soil when we use one of these penetrometers. And I think they're fine for usage on a particular day, comparing one area of a field to another area of the field where those areas are at the same moisture content. But we've seen some widely kind of misleading information that we've gotten from these penetrometers. And we've done some work and looked at some other studies. And this is, I think, one of the most helpful studies that we found. And this is looking at penetration resistance on the y-axis as a function of soil moisture, and the frame on the left, or degree of saturation on the right. And these are different soil types. And you can see what a difference just a small change in volumetric water content or soil moisture makes for penetration resistance when you look at some of those curves on the left. And I think this is especially true within our clay soils. So really just advise moving forward with caution. You can use these tools, but they just need to be used with a good understanding of how moisture status is going to affect the information you get from them. Because of this, we've actually started to do a little work looking at other tools for measuring compaction, electromagnetic induction and ground penetrating radar. We trialed these this past fall with Olga Vargas out of NRCS in New York. Brought over these really cool, like lawnmower-like tools, which you drive over this, push over the soil. And we kind of, I think, established a proof of concept here. This is a aerial view on your top left of a cornfield where we're half in the headlands and half out of the headlands. And then you can see the electromagnetic induction readings on your right, where we see the more compacted soils, or the blue colors in the headlands versus the browns and the greens of the lower compaction that is existing outside of the headlands. And then we also, that was the EMI data, and we've also used some GPR data, ground penetrating radar, and this is showing the kind of the more yellow and red colors are indicating a more compacted soils. And this is on the left half of your screen. Those are the headlands where we're seeing that compaction there, versus the right-hand side of the screen out of the headlands, where we're not seeing those red colors, those yellow colors. And this needs a lot more work. There are some natural existing kind of dense layers like the argillic horizon that's shown here that we have to do some I think ground truthing for before we start to use this tool widespread, but we're excited to do some more work with this and test some of these tools that are being used in Vermont for alleviating compaction, some of the deep subsoiling tools and such, and maybe use this to evaluate those. Okay, and now I want to talk a little bit about the dark side of soil structure, as I call it, and this is preferential flow, so we can have really well structured soils, and that's fantastic, and we have really well aggregated soils. But what happens when we do that, we start to change the way water moves through the soil, which can be a good thing, but also can result in some unintended consequences. So this is a infiltration ring. These are images from a former lab at Cornell, and you can see that in the upper soils, this blue dye that was poured onto the ground infiltrated somewhat uniformly, and then it found some of that structure, some of those macropore spaces, and moved very rapidly down through the soil. And you can see that streaking below the upper root zone where that water moved very quickly. This is just a result of really what we're doing to improve soil structure, which is a fantastic thing. We have these networks of old root channels and insect or earthworm burrows and such that create these biopores that can rapidly move water. We also see these naturally occurring in some of our expansive clays where we see cracks forming. And I think what we're watching really closely is as we develop soil structure, improve soil structure, are we seeing rapid transport of water to underground conduits like tile drainage? So this is something we're putting a lot of doing a lot of research on and hope to understand better if this is happening in really healthy soils and well-structured soils, what we can do about it. How can we manage for this unintended consequence of soil health? Okay, and my last topic here is available water capacity. And I think this is really important to touch on given observed climate changes in Vermont. And we are definitely getting wetter in the Northeast, but the pattern of precipitation is such that we're seeing very heavy rainfall events interspersed by maybe weeks on end without any rainfall at all in some, not in every season, but certainly in some seasons. And this is a nice figure that was produced almost 10 years ago now, but looked at, because of a changing climate, what the irrigation demands would be within every state in the country in the future. And this is comparing 2090 to 2005. And I've circled Vermont there. We're right in the middle of the pack. And this is predicting that because of these droughty periods, irrigation withdrawals will need to increase by about 1.75 times by 2090. So roughly about a 1% increase per year. And so because of this, I think it's really important that we understand available water holding capacity and how to improve that, especially in our specialty crop production, where some of those crops are less resistant to drought than some of our field crops. And so I'll start with some important terminology here. So field capacity is really the point at soil moisture, point of soil moisture where water has ceased to drain via gravity. So we have a rainfall event and water drains from that soil at the point where that stops because of gravity. That's called field capacity. And then water that is held within that soil down to the wilting point or permanent wilting point, that's the available water capacity. So we have this range between field capacity and permanent wilting point. That water within that range is what's available to our crops. And so here's a visual of that same concept with gravitation or free water drainage occurring on the right-hand side of the screen, where we have a saturated soil, water is draining out of the root zone. Where that stops is when we're at filled capacity, that dashed vertical line. And then what's in the water then, what's in the soil, the water in the soil then is capillary water. And that's the water that the plants can use. That's the available water capacity of the soil, and water below that. It's still there in the soil, but plant roots cannot access that water. So that's when we hit our permanent wilting point. I think it's important to note that this soil health indicator, this available water capacity, also has some a controlled soil texture at very coarse soils and very fine textured soils. We see a much tighter range of available water capacity. And then really in that sweet spot of loams and silt loams, that's where we see a greater degree of available water capacity and really potential for available water capacity. Again, these soil texture factors have set guardrails on where we can go with some of these soil health indicators, and this is a very good example of where they ultimately control the maximum available water capacity we might be able to achieve with all of the soil health practices being used in a very healthy soil. So how does soil health and aggregation affect available water holding capacity? It really does in two ways. One is through the formation of soil aggregates. Allows for water to move vertically down through the soil in between those aggregates, creates those large pores for water entry to occur. And then with those micropores that I showed in my first few slides, those micropores are critical for holding water so that there is more water available and growing that available water capacity for access for plants during droughty periods. So it's really, the organic matter that is helping to build the aggregates, and the aggregates that are creating the pore spaces to hold that water. That is really the critical factor here in terms of available water capacity. And then finally, I think this is my last slide. Many of you have probably seen data like this before, where available water capacity, to what degree does available water capacity increase as a function of increasing organic matter? And I'm showing this here for three different soil texture types. And we're seeing anywhere from a 0.8% increase to a 1.13% increase in available water capacity with a 1% increase in organic matter. And then if you follow those to the right, you can see what that means in terms of actual volume gallons of water for that particular field and crop. Okay, I made it through that without a problem. So I think we do have some time for questions, and glad to take those.
Great. Well, thanks, Joshua. Yeah, no technology issues. So perfect. If there are any questions for Joshua, please type them in the chat and we'll get them answered. And we also have the QR code that Sarah or Susan will put up for people to scan for your CCA credit here in a minute. Joshua, I was wondering about you were talking about intermediate, small, large pores. And I'm just curious, with all the different measurements that people do on aggregates, are they measuring different sizes of aggregates, or what's going on with that? I guess I didn't hear much.
Yeah, great question. I should have talked more about that. So of the methods I mentioned, and I didn't show a picture. I didn't have a good picture. I should have. None of those except for one method really tries to understand the different aggregate size classes within your soil sample. And so one method does, and that's actually the method we're using. We're developing and not developing. This is an established method, but we're developing for use within our lab here at UVM. And it stacks different size sieves on top of one another. And then it dunks it, they're submerged within the water, and they move up and down very slowly. And then when we remove those sieves, we can dry those different size sieves, and we will have a measurement of what the different size aggregates are. Difference, I think there's 4 or 5 different classes that we'll be able to report on. So I think that's something we're pretty excited about, is that we won't just be able to provide people, a single number for aggregate stability, that we'll be able to provide a little bit more information about, well, most of your aggregates are in this size class, or here's the spread of the size of your aggregates.
Right. Yeah, I was kind of wondering, because I think some of the tests just report on the bigger aggregates. But I'm assuming, based on your presentation, we want all different sizes of aggregates.
Yeah, I think there's a limit to what we, in terms of micro aggregates, we can only go so small. But it would be wonderful to get, from as small as we can measure to as large as we can measure. I think that's important to see. And I think we'll know more about what that means, hopefully, as we move forward with SHREC and more data in Vermont. I'm kind of excited about that. I haven't seen a lot of work on that.
Yeah. I just quickly, for folks, we do have another survey that we would like people to answer to get more feedback. So if you do have time, there's a link, and also a QR code if folks don't mind answering some more questions for us. We have another question from Sarah. When you're trying to reverse compaction, what do you think the most effective, what would be the method most effective of adding organic matter? Should you till it in, or do not till? Does it take much longer not tilling, or maybe it depends? So organic matter to reverse compaction.
Yeah, I actually had a conversation about this yesterday. I think it depends is probably the safe answer. There's a risk of, if with tilling it in, that you do more damage than good. You do more bad than good, but I don't think that's necessarily always the case. I think if a soil is very degraded, that getting that organic matter incorporated, especially if tillage is already going to occur, that's probably the best course of action. If we're looking at a soil that is really well structured and pretty healthy, I think it would be risky to till that organic matter in, that it would probably be best placed on the surface. So I don't know, Heather, you may have some thoughts on that too.
Yeah. I think that sometimes people often think that adding organic matter will alleviate compaction instantly, and I think that's not necessarily true. It feels like a method to build soil structure, and it takes a little bit of time to do that, but I don't know. And building soil structure can help build the resiliency and sort of resistance to equipment and animals and compaction. But I don't know, and correct me if I'm wrong, Joshua, I'm not sure if it really alleviates it per se, or does it?
Yeah. I mean, that's a good point. I think that's fair. I think it helps build resilience to it, but doesn't necessarily, it's not going to be a prescription for it. necessarily. Yeah.
Yeah, I think that's where all of this gets kind of complicated and
Yeah.
tough.
Yep.
It is
Yeah.
depends. Okay, so Deb has a question and she was wondering if you could speak a bit about whether aggregate stability size classes are possible to assess in heavy clay soils of Vermont. Seems like there could be some confounding there.
Yeah,
Sounds like it by his laughter.
that's a great question. We gotta love these clay soils. Yeah, I mean, I think we've gone round and round about this, where some of the standard methods require, sieving soils to a certain size. And in our clay soils, that may result in kind of destroying some of the aggregates. So this is a really tough nut to crack. Thanks for putting me on the spot there, Deb. We're continuing to work on this one.
Well,
Yeah.
I'll just chime in here a little bit, since some of our experience has been it's been pretty difficult, and so one wonders, I'm thinking that perhaps it's not as so useful to run that on the really heavy clay soils, just because we're not sure how reliable those results really
Yeah.
are, just because of the difficulty of kind of separating those into parts, so
Yeah.
the aggregates might be, they're easier to measure on some of those loamy or lighter soils for sure.
Yeah, I think that's, it's like all these things that happen in the field, we're trying to somehow measure them in a lab, and there's always going to be some limitations to what we can do. Yeah. Yep. Yep.
All right, well, there's another question about freeze thaw cycles. So our annual freeze thaw cycles, and can they help alleviate compaction in the depth, at least, of animal hooves?
I've never measured that, but I think that makes a lot of sense, that some of that can happen. We certainly see freeze thaw cycles can also damage aggregates as well. We certainly see that happening. And so I don't know of anything. I can't think of any paper or study that specifically investigates that, but logically, I think that it probably is possible for that to occur.
All right, one more question, and that probably will bring us to the end. Can you explain the permanent wilting point one more time?
Yes.
That's water below field capacity?
Yeah, sorry. I know these concepts are difficult to explain. So yeah, permanent wilting point is when the plants have removed all the water from the soil that they can. So if you think about them, their roots being little pumps, they're pumping water out, but at some point the soil pores are holding water so tightly that they just can't pull any more water out. And that is permanent wilting point. There's still water there, but it's held so tightly within the soil pores that the plant roots cannot access it.
Okay. Well, we are at 12:59. And I want to thank you, Joshua, for your time today. That was a great presentation. And I know I learned a lot, so thank you so much. And hopefully everyone else learned a lot too. And tomorrow, as already mentioned, Deb Neer will be joining us and talking about biological indicators. So even more discussion around soil health and indicators. And I would say it may get even a little more complicated because there is a lot of biological indicators that can be measured to evaluate soil health. And I think Deb's gonna try to give us an overview of some of those and what's most important for us to be looking at. So again, thank you so much. If you have time, please take the survey if you can. And I see Paul left a note asking about PFAS contamination and wondering if that's going to be added to our list of soil health stats. So that's a good question, Paul. Something we've all been talking about with the new soil health lab. So maybe if Deb has time tomorrow, she can comment on that. All right, everyone, have a wonderful day. Thank you very much. And we'll see you tomorrow.